Hi and hello everyone. Good evening. So today we are going to discuss about TCP Keep Alive, and we'll do a lab for TCP Keep Alive, and we'll discuss about what is Gracious ARP and how the Gracious ARP helps us to find the duplicate IP address in the network. And we can see the same in the Wireshark and how Wireshark is interpreting the duplicate IP address. Then we'll see what is window size and what is the difference between window size and calculated window size, and what is window scaling factor. Then followed by that, we'll see what is fast transmission. We know about retransmission, and we'll see what is fast retransmission and when exactly the fast retransmission happens. And we will see the use case for a busy server, how we are going to find the server is busy and it cannot process a client request, and how we can do spot the problem is with the server. And followed by that, we see the use of TCP timestamp, and we'll have a theory and lab for the same. They're using the TCP timestamp, how exactly we can spot it is a problem with that client, and how we can spot the client slowness with TCP timestamp. Then we'll see the use cases for Wireshark images, where we can exactly spot where the problem is and how exactly it says it's retransmission, duplicate acknowledgements, and how exactly the TCP buffer works. So we will see about, we'll look into all the possible errors, TCP errors, bad TCPs, and how we're going to spot this with Wireshark filters. And then the final part is the DUPAX and fast retransmission. We'll see the use case for both DUPAX and fast retransmission. So let me start with TCP Keep Alive. So I'll give a background about TCP Keep Alive. So what exactly the TCP Keep Alive and where exactly it comes. Let me open up my Paint. So this is my client and this is my server. So we all know, we are much familiar with this. So we know SINAC, ACK. So this is the successful TCP connection establishment. SINAC and ACK. Now there is a successful three-way handshake happened between client and server. So now exactly the actual payload that's being streamed. So let me name this as a stream 1. And stream 1, and this is a telnet session between these servers. So let me draw one more line here. We'll also see the same thing in Wireshark. This is stream 2. This is the second telnet session. So we call everything, I mean, we call the one if a connection establishment happens, and if your actual payload that's been exchanged between client and server, and if it is a one connection happened, then it is a stream 1. And if you're trying with a second telnet session, it is your stream 2. So that's how Wireshark is going to differentiate the TCP streams. And now, okay, so now this is a stream 1. I'm sending a payload. So now I'm going to drop 2 more boxes. So the very vital thing the TCP that manages is called the buffer, TCP buffer. So window size is the very first time when it's in the SYN. It's going to say my window size is something around 165 bytes. So where the scaling factor fits in here. So scaling factor is something, okay, I'm now my buffer size is 165, that's my window size. So I keep this copy, even though if I send a data, I'll keep a copy of it. So once I receive an acknowledgement, my buffer is overwritten with the advanced sequence numbers, right? So that's how the TCP buffer maintains. So now the window size is 165. So scaling factor is a multiple of the window size. I'll show you that in the Wireshark. So it's also example, if I want more room for a data to send, my window size will keep increasing like this. So my buffer size keep increasing. So it can be in the beginning, it can be 165 bytes. And it may increase somewhere around 65,535. So in the same way, you got a buffer on the other end. 65,535. And once it fills up the whole buffer, we see this window 0. So it's 0 window size. The same applicable for the receiver, the server. So this how you have to visualize how this buffer, the buffer, the congestion window and all this is calculated based on this. So this is the buffer. So whatever the data it sends, it keeps in the buffer, and the buffer will be overwritten based on if the T sequence number keep advancing, and if I'm not if I get acknowledgement for all this packets, whatever I send from source to destination. So the buffer will be overwritten with the advanced acknowledgement, advanced sequence packets. So keep alive, where comes the keep alive? So example, in the stream one, I send a SYNAC ACK, I got it. So my payload exactly happens here. So my TCP segment length comes here. So I'm sending a payload of TCP segment length, and it is a telnet session, and user is typing something, doing some config change, and something is 78 bytes. So what is my sequence number here? Example sequence, random sequence 7890. So I send the sequence number now. For that, I get an acknowledgement back from the receiver. For this sequence number 7890, I got an acknowledgement back here. So acknowledged 7890. So now what happened here in the telnet session, the user is here. The user is not typing anything and he is waiting. So what exactly happens? The TCP RTO, it is request timed out. So the TCP timer will start, the stopwatch, it starts here. So it is purely managed by TCP stack. We have no control about that. So if the RTP expires, the retransmission happens. But instead of that, I established a connection, but I didn't get an acknowledgement back. So maybe my acknowledgement may be lost somewhere in the network, or I haven't received the acknowledgement, it is missing. There comes the TCP keep alive. So it's going to say, the sender is going to say, hey, are you alive? It's going to say, are you alive? And if I get for this TCP keep alive, I should get an acknowledgement back again. Acknowledgement. So once I receive that, okay, the sender thinks, okay, still my connection is active. User is not typing anything. I have to wait and it will wait for it. So even though RTO expires, but still the TCP key, with the help of TCP keep alive, the session is still open and it will wait for some time. So it's again managed by TCP stack, and it means that my connection is still active and the user is, it's a no human interference where the user is wants to type something and he's making a delay here. It is not the actual TCP delay. So this is how the TCP keep alive works. Now let's go to the lab. So to create this, I have created a very simple lab. So here I'm I'll open up my paint. Here I enabled a telnet session. Here is my telnet. So my TCP connection establishment happens here. So I'll log into the boxes. I'll show the config. The topology is pretty simple. So I have assigned a point-to-point connection. So I have assigned 20001 for fast Ethernet 0/0 on router 2. So this is IP address assigned for router 2 on fast Ethernet 0/0. And this is just a point-to-point connection. So it's /24. And if I go to router 1, so 1 interface. So it's 20001 and /24. Let me check the IP connection. If I do a self ping 20001, I can ping. If I give show IP ARP, and I can see an ARP for 20009. So TCP keep alive. So the command is service TCP keep alive in and out. So I have to give this command on both router 1 and router 2. So I'm enabling the keep alive globally. So warning includes service. So it is enabled. So the command is simple. You have to go to global config mode in Cisco boxes and you have to give service TCP keep alive in and out, both for in and out. Should be opened. And you can check your TCP connection. The command show TCP brief. Since I haven't established any connection now, so now let me try to establish a connection on R2. So I enabled telnet and I have set a password Cisco default. So one include user. So I've created a user, privilege level 15 and password is Cisco. So one include enable password. So enable password is there. So now let me try to do a telnet session. So for that, I have to go to R1. Let me try to ping 20009. So if I show IP interface brief, I can ping 20009. I'm going to do a telnet for 20009. Let me open a capture. So I'm capturing your traffic on fast Ethernet 0/0 on R1. So it says it's telnet. So telnet connection is done. I'm in boot and fin, and I haven't typed anything. Let me initiate a telnet again. And I give a password. Enable Cisco. Now my connection established, and let's wait for a few seconds. I'm not typing anything. And also in the meantime, let me check in the router, show TCP brief, and it says connection established. This is my IP local, and this is the remote IP address. This is the port number, source port number, and it says the connection established. And if you in the router, you can see more details about TCP. If you give TCP address and the value given here for the established connection, the router will tell you, okay, what is the, okay, it sends a 9 retransmission, 27 keep alive. If you actually see here, it's my TCP keep alive. So I didn't type anything. So the session is opened and it says, I get a TCP keep alive from the destination 20009 to 20001. After, if you look at this, if you exactly look at the TCP keep alive, it's waiting for 2 seconds, nearly 2 seconds, and it says the destination, it says, hey, are you alive 20001? You want to type something? I'm waiting for you. Then again 20001 is saying, hey, I am alive, don't close this connection. And still the connection is opened. So once I start typing again, so you can see the number of keep alive packets sent. And you can see your retransmission packets, and there's a couple of useful information you can make use of this. And if I keep typing, you can see still the connection is open. Let's wait for some time. So I close the connection now. Oh, sorry, we stopped the capture. So we should see the fin packet. And if you go inside the Wireshark, you can see this is TCP stream 0. If you see this is a second telnet connection I opened, and you can see the stream index value is 1. So this is my second telnet connection. This is how the Wireshark distinguish your connection. This is stream index 0. This is my first telnet session. No keep alive. But here I established a connection and I'm waiting for some time. I didn't do anything and I get a TCP keep alive. This is to make the session active even if I am not typing anything. Both end it says, are you alive? And the other end says, yes, I am alive. This is how the TCP keep alive works. So next, we'll see Gracious ARP and how Gracious ARP works with the duplicate IP address. So I want to give a background about what Gracious ARP. So again, first a quick refresh about ARP. So I got 2 layer 3. One is 10.0.0.1/24. And the other layer 3 is 30.0.1/24. So I got here as 40.0.0.1/24, 50.0.0.1/24. So I got 2 PCs here. So I connect this PC on 30 network. So my IP address would be 30.0.0.5/24 and my gateway 30.0.0.1. Well, let me differentiate with another color here. So my gateway is 50.0.0.1. 50.0.0.2/24 and my gateway would be 50.0.0.1. I got a connection like this. And now the point-to-point connection between these two routers. It's on 10 network. So 10.0.0.1 and the other end here. It's 10.0.0.1. Other end here is .2. So this is a point-to-point. So this is how my connection is. So what happens here when we do an encapsulation, and if I want to send a ping, the very first thing what happens here, to send a ping, I want source IP. So my source is 30.0.0.5. Layer 3, destination IP is 50.0.0.2. Source MAC AA, for example, destination MAC DD. So let me mark here. My MAC is DD and this is AA. So I don't know the destination MAC address. Always we know the layer 3, but we don't know the MAC address. Why? Because I am on the local LAN. I don't know the destination MAC address on the remote end. So how I'm going to find the destination MAC address? So here comes ARP. ARP request is a broadcast. What is it inside the ARP? So it says sender IP, .30.0.0.5. Sorry, here I mentioned 30.0.0.4. And destination IP 50.0.0.2. Source MAC. I know because I'm sending a broadcast. AA and destination MAC is layer 2 flooding. All F 16 bits. This is called ARP broadcast. So this all happens here. So for my ARP request, here it's going to check, okay, it is in my local domain. So do I know the MAC address here? The switch says, I don't know the MAC address of this device. So who is going to respond for my ARP? So since this is a broadcast, so except the incoming port, it goes for all the outgoing ports. Here on all the outgoing ports. And this particular network 10.0.0.1, because we got two active layer 3 here. So this particular network, it's going to say, hey, my Ethernet MAC address is GG. So you can send me this packet back to me. For this ARP request, I'm going to get an ARP reply from this 10.0.0.1. So this is the ARP request. This is all the information we got. And now the destination MAC, instead of FFF, it's going to put GG and forward this packet back to here. So this is going to say my MAC address is GG, you can send this. And this ARP reply is a unique cast because I know the source MAC address. Because here in the ARP request, if you see, I know the source MAC address. So only here the destination MAC address is unknown, and now I got the destination MAC address and forwards here. So again, what happens? It checks inside the routing table. This router, it checks inside the routing table. And do I know about 50 network? Because it says 50.0.0.2, and in the route table, we know there are two values, that is RIB, routing information base, and FIB. forwarding information base. So let me give you a little background about that. So fib, it maintains an adjacency table. Why it is used? Because every time for the ARP request, the router has to respond, but instead of that, they have a specially designed chip, Ceph. Why I'm saying this? Because this is how the ARP works in the boxes in the network. So let's see how the Wireshark is going to interpret this values. So inside this Ceph, this is ASIC chip, the specially designed chip. So where you got your adjacency table and your forwarding table. Forwarding table is your layer 3. Adjacency table is your layer 2. So inside the adjacency table, you got your layer 2 information, way to forward the package. Okay, if this is the very first ARP request, so it is, I don't see this MAC address inside my fib. So the router is going to respond this back. And once I got the MAC address details, it's going to, keep a copy of it as a cache. It keeps inside. So next time when this same PC is going to send a reply, if it wants to communicate to 50002, it's going to look at inside the adjacency table for the MAC address, and for layer 3 forwarding, it's going to look into the forwarding table layer 3. So this is the conventional way how exactly the ARP works. This process keep happening until it reaches the destination. This is how the complete flow of ARP. So now ARP is done. So what is gracious ARP? So let me make it as GR gracious ARP. So it helps to find the duplicate IP address in the network. So every time if I assign an IP address to this PC is going to say, hey everyone, no one should use 30004. I have assigned. And it does a broadcast to all the IPs. It's a broadcast, right? So it's going to send a broadcast to everyone in the same broadcast domain. So I have assigned this IP address 30004, 30005. Broadcast to everyone in the broadcast domain. So what happens? No one should use it. So if I have one more PC is connected here, if I bring in one more PC, and if I connect to the same TIN network, and if I assign the same IP address, the gracious ARP comes in and it says, hey, I found a duplicate IP address in your network. So it helps to find the duplicate IP address in the network. So let's see in the lab how exactly the gracious ARP works. So to do that, let me go here and let's take a look about the topology. So it's a fast Ethernet 1/0 on router 1. So I'm going to router 1 and I'm going to see show IP interface brief. And my fast Ethernet 1/0, I have assigned 10 network here. So I have assigned 10.0.0.7. So what I'm going to do, I'm going to stop this capture. I'm going to start a capture here. Open a Wireshark. So it is between PC1 Ethernet 0 to router and fast Ethernet 1/0. Okay, exactly. We have to look at here. Let me close this talent session. So now what I'm going to do, I'm going to see the IP assignment on the PC. So in the here in the PC, if I give show IP, so I have assigned 10.0.0.7 and my IP address is 10.0.0.4/8 and my gateway is 10.0.0.7. So my gateway is 10.0.0.7. So now I'm going to assign an IP address as a 10.0.0.4 here. Let's see what happens. IP. So if I give the same IP 10.0.0.7/8 and my gateway is 10.0.0.7. And gateway, I think, wait, let me check this IP address here, 10.0.0.7. So what is my IP show IP? My IP is 10.0.0.4. Okay, let me go and assign this IP address on the router. IP address 10.0.0.4 255.0.0.0. Let me check the separate mask once. Okay, it is /8. Interface faster than 0/1. IP address 10.0.0.4. So pass 255.0.0.0. So I got a gracious ARP. It's a reply from 10.0.0.4. Let's wait for some time. Now let me go to the PC and let me try to ping 10.0.0.4. I can ping. Now let me go and shut down and re-enable this interface. Shut. No shutdown. We should see a duplicate IP address, the gracious ARP. Show IP interface brief. It's 10.0.0.4 on both ends. So now let me try to assign an IP again. IP address 10.0.0.4/8 and gateway. Let me put this as 10.0.0.7. Now this PC is saying that this is a duplicate IP address and I should see a gracious ARP reply with duplicate IP address. Config. With no shit. So I cannot, it says its IP cannot be changed because that's been used by a different MAC address. So I cannot assign this IP address here. So the capture is going from PC0 to router fast Ethernet 1/0. Let me go back to the topology. Top. Again, start the capture. No IP address. Show IP. This is not allowing me to assign this. Let me try here. So I cannot assign any IP. So if I say IP 10.0.10/8, the gateway, let me say 10.0.0.7. So when I do this, I get a gracious ARP request and it says it's 10.0.0.10, that's fine. If I go to a router and if I assign the same IP address 10.0.0.10 to 55.0.0.0, so now it's showing. I don't know why I don't see that before. Fine. So it says it's a duplicate IP address, right? So it's also in use by this MAC address. If you go here, 6x80. So GNS is not so accurate like the real boxes. So sometimes you have to replicate twice. It depends. And show IP, it exactly says this MAC address. Say 6800. This is using the same IP address, and this is a duplicate IP address. This is how the Wireshark is going to say about this gracious ARP. It says this is a duplicate IP address. So if your connection breaks somewhere, you have to look at your ARP, and the gracious ARPs are going to tell you the duplicate IP address. So let's see from the router perspective what we would see here. Show logging. Here nothing it says about the duplicate IP address. So only possibility is with Wireshark, it shows the gracious ARP and it says duplicate IP address. And I think you can use your debug ARP. Let's say debug IP ARP. Debug IP debug ARP. Debug ARP database. Debug ARP table. logging buffer. So logging buffer, let me give value of 4096, a minimum logging buffer value. I'll give terminal monitor. Okay, console shows me the error, but I don't think we see errors for this. So now let me try to ping 10.0.0.10. I get successful reply. So it says, okay, in my R database I found, and show IP, save, recency, interface, show IP, save, fast Ethernet. Where is my for 10.101? Recency, interface, one, and detail. Okay, next hop is my next hop. My IP address is this PC 10.00.10. So no adjacency, it says. Show IP safe. For 10 network, this is locally attached, and this is forwarding information base. And it says it's a directly connected, and I don't see any further more details for it. Okay, so the ideology is just I want to show you what is the forwarding information base, and I would like to show you the MAC address. But anyways, this is a duplicate IP address, and we don't see this in the ARC cache. So that's how Wireshark is going to say this is a duplicate IP address, and you can figure out your duplicate IP address in your network if you have any VM or anything where I had a problem with a VM. They assigned a duplicate IP address, and it's very hard to find that. But with the help of Gracious app, you can find the duplicate IP address in the network. If somebody is using in the same broadcast domain, it's going to say the Gracious app and say, no, this is being used by someone else, and you cannot assign this IP address. So that's it about Gracious app. Let's move on to window size and calculated window size. So yesterday there was a question. So what is calculated window size? So let me close this capture. Let me go to GNS and stop this capture. Stop. Let me open a trace file. Let me take a capture. So here, if you look at this value, TCP option. So the window size here, it says 65,535, and the calculated window size is 65,535, and that can be scaled, and you should multiple the value by 32. So let's see what is in this. So it is same. So it is not sending any more data. So let's go back here. So if it is -2, no window scaling is used. So here actually, if you look at this, my window size is not increasing at all. So sorry for that. This particular capture, we cannot find exactly the calculated window size. Let me take one more. Okay, here I see a different window size values. Let me delete. So, okay, in the very first send, it says, okay, my window size is 8192 and calculated window size and option and scaled by 4. So this is the very first packet, SYN packet, right? So I mark this with blue color for all my SYN. The SYNAC and ACK, here exactly the window size is being increased. Scaling factor is 4. So now let me take a calculator. So 16425 into 4. Okay. So let me show you this. So scaling factor. So my buffer here, if you go to my buffer, this is TCP buffer. And in the very first proposal, the SYN, it says my window size one 16425. So the total buffer value is 16245. That's the amount of data I can hold in the buffer. If I get an acknowledgement, that's overwritten. So my buffer size is 1645. Sender, it says, and I can scale. I can, expand my buffer 4 times. If you see the scaling factor, it's 4 times. 4 times of the current window size. So it can scale 4 times. If you calculate the same thing in the calculator, so 16425. So for that it says 16425. 16425 into 4. That gives me a value of 65,700. So now my buffer has been increased to 65,700. Earlier it was 16,425. And now my buffer is 65,700. So now more room. So this is how exactly the window scaling is about. And the maximum buffer it can hold, even if you run, as I said yesterday, if you run your 10 gig link, my maximum buffer size is 1 gig. And we all know that the TCP stream happens segments by segment. It's not happening in a one single flow. It's going to send the segments, and for the segments it mark with the sequence, and if my sequence numbers keep advancing, then all looks good. So I'm going to chop the data and send it as a sequence number 125, say, share 500 MB of data, then sequence number 7685, send another 500 MB of data, right? So that's how it just sends us a stream of data, not as in the one single stream. You're not sending back everything, because if something is lost in the middle, we cannot track that. So that's the mechanism of Wireshark. And now this is how the TCP window works. You can do the same calculation. If you practice, you'll get to know about that. This is exactly about TCP window size and window scaling factor. And for this example here, my window size is 16. That's my calculator again. Let's do 16408 1648 into 4 equals 65632. The same value you get here. Multiply the value by 4. So this is the calculated window size. with the help of, not with the help of with the scaling factor, you get your calculated window size value here. If you see on all your view packs, the window size is not increasing. What is the meaning of it? So my sequence number is not advancing. There is something problem in the middle. So that's how you can figure out exactly. If you use SAC, I'm missing a sequence of 5841 to 11681. Exactly, you can see here. Sequence number 5841. So this is missing. So it says previous segment not captured. Who's telling that? The server, it's telling previous segment not captured. Your FTP data, I am missing it from your end. It's a client. It says previous segment not captured. You have to send this 5841 back again. So once it receives this, the duplicate acknowledgement stops and the stream continues sending the data. So the key takeaway is you should understand everything and you have to do a lot of practice. Only then you can figure out what is window size, what is calculated window size, what is dupacks, why, what happens exactly with dupacks, and what is selective acknowledgement. If you do more labs, you get familiar with that. So now let's see what is fast retransmission. So I will give you a visual about what is fast transmission, fast retransmission. Same thing here, you can go to this website for the link. I'll share with everyone. You can refer this. So in the paint, we discussed about how, okay, what is a retransmission? So I'll give you a glimpse again. So when it sends a data, SYN, for my SYN, I should get a SYN back. So when I send a SYN, it starts the stopwatch, the timer, and it is maintained by TCP. And once the timeout happens, it's going to retransmit the data. So this is called as retransmission. Right, so this is sender and this is a receiver. Retransmission after timeout in the buffer. So it's going to start the stopwatch, and if the segment is lost, it's going to retransmit. But what is fast retransmission? Somewhere we see fast retransmissions. Whenever you see 3 duplicate acknowledgement, so it says segment 1, it's sent, and I got a acknowledgement back. But it sent segment 2, it is lost. I didn't get the segment 2. But I sent segment 3, I get an acknowledgement. For segment 4, I got an acknowledgement back. But for this last segment, the 3 duplicate acknowledgement, it's asking for segment 2. Hey, I lost the segment 2. So my full packet is all 5 segment has to be received. If not, using the selective acknowledgement, I'll get it. So inside the do pack, we have seen many times that you see the selective acknowledgement and I lost only this particular segment I lost. Can you retransmit this back? This is how the selective acknowledgement works. And if I see 3 consecutive duplicate acknowledgement, the fast retransmission happens. So it retransmits the segment 2 without waiting for its timers to go off. But whereas in the retransmission, it will wait for the timer. But here, instead of waiting for the timer, okay, I received 3 duplicate acknowledgement. It says, okay, I didn't get an acknowledgement for segment 2. Okay, I think somewhere in the middle in the network, the acknowledgement is lost, so I have to send this. So that is called fast retransmission. That is a key difference between retransmission and fast retransmission. You should know the difference, and you can go through this. This is a very good website where you get an explanation for this retransmission and fast retransmission. This is a use case. So solve, we know if you see multiple duplicate acknowledgements in your capture, so you should straight away you have to spot, okay, there is a retransmission happen, so there should be a selective acknowledgement, there is some packet lost in the middle. And if you see a lot of dupacks, then it's a problem with the network for sure. And you have to see who is sending the dupacks. Right, then the sender is a problem. So there is something in the middle. You have to look into your topology, end-to-end connections. You got your 4-5 hops. You have to check your FCS. Somewhere here, your FCS counter is increasing. Show interface status will give you the errors. So you have to look in your topology, YP interface brief. You can see errors, output errors, input errors. It's not increasing, CSC is not increasing. Then if you see a lot of dupacks, you have to scan and you can walk down to your network hop by hop, and you have to see where you can see the FCS error increasing. Definitely you can spot somewhere in the middle. So it depends on how much dupacks I receive. So if you hardly receive 1 or 2 dupacks, that's common. That happens with the very minimal latency in your network. So that is about fast retransmission. And now let's see the busy server, how we can say spot this is a server issue and this is not a client, how we can exactly spot. So I'll give a little background about the busy server here. So again, this is sender. And this is receiver. And the same things, I get send, SYNAC, ACK. Successful connection establishment happened. TCP established. And the very key thing you should look at your capture always is RTT, round trip time. Here, RTT, round trip time, bidirectional, Wireshark capture on both ends. So round trip time. So if I see, so what is RTT? If someone is asking what is RTT, is the time taken for my SYN, I should get a SYNAC back. So the time since I send a SYN and until I get a SYNAC back from the receiver. So that is RTTs, how long it takes from my source to destination and destination to source, vice versa. So that is RTT, round trip time. So you have to spot if you see exactly the RTT time is increasing. The human delay, exactly they can spot if it jumps beyond 1 second in the network. Well, 1 second is too slow. I mean, not slow, but it's a bit slow, I would say. 3 seconds, 4 seconds is very slow connection. So it all happens in microsecond and milliseconds. So you have to look at your RTT on both ends. Is it increasing? Is it going beyond 2 seconds, 3 seconds? And if you see there, you can spot and it is a network. Okay, now the scenario is, now my RTT is perfectly normal. It's all happening in milliseconds. I don't see anything that jumps beyond milliseconds. but still I see slowness here. Then how I can find out? There's an option in Wireshark that is called TCP timestamp. Let me open a Wireshark for the same. This is for fast retransmission, and this is a capture for a busy server. So for this color filter, go to view, coloring rule. So I made all the sin packet with blue color for identification. It's a sin. So it's going to say, see, I send here. Let's look at here. So what is TCP timestamp? If you actually see all this values that is matching my TCP timestamp, it should match. Only then your capture is you have done your configs properly on the Wireshark. So you have to ensure that. So what is the exact packet I have to make it as a filter, as a column? If you go to timestamps, so these are all the values, this block values that's generated by Wireshark. So if you look at this value, so let me come back here. Time since previous frame. This is the exact value I applied as a column. So now the difference. RTT is the time taken by the network, and TCP timestamp is the TCP actually takes a time for my TCP streams. That is not related to RTU. But if you see your round trip time is 1 second, and if it is going beyond 2 second, 3 seconds, then it's a problem with the application. That's how you can spot. See here, my round trip time is very normal, right? 1 second, 1 second. So here exactly the client, it is taking 12 seconds to send this data. It's happening on TCP. Sorry for that, I'm scribbling a lot. So let me mark this. So this is client and this is server. So my RTT looks good. But for my request, I send a request to this server. But the TCP stream, it gets 12 seconds because the user is not typing anything here. Or maybe the user typed and the server is busy accessing the same request for other clients. So with the TCP timestamps, you can figure out that, and you can drill down what is their highest TCP timestamp. Here you have to sort the value here. It should be in the up arrow. And this is your longest TCP connection. Can you see this? How I spot this server? Because see, I am retransmitting a packet again and again. I am doing a retransmission. Client is retransmitting. And then after 12 seconds, I get a response back. I mean, the client send the data back to the server. So retransmission is happening from this client end. The server is busy. So, hey, can you acknowledge me back? The client is asking, but the server is saying, no, I'm processing other TCP connections. So you have to wait. Then the client is again retransmitting. Okay, I'm sending a payload again. Can you process my TCP? That's how the retransmission happens. And after 12 seconds, the client could successfully send the data. So now we can say this is a busy server. The server is busy. So I'm retransmitting. So you have to do a lot of use cases and you will understand about this. But the key thing is, okay, what is the use of TCP's timestamp? This is how you can find your longest time taken, longest TCP stream. I mean, where in your capture you can figure out. If you look at this, there is no retransmission happen from the server. So it means client is good. Client is acknowledging back for every send and the payloads. This is how you can figure out if the busy server in your use cases. If you encounter the same problem, you can compare and you can look for options and you can figure out. So this is about busy server and this is a use case for it. So the next topic is use cases for Wireshark. I found this is very useful, so I would like to share this. So let's see. So here it says 10.3.30.1. Here 10.3.30.1. See, it is retransmitting. Segments number 5841 again and again and again. When the request timeout expires, the stopwatch expires, the TCP algorithm is used exponentially to increase the retransmission wait time. So it keeps retransmitting because I am not the stopwatch started and I am not getting an acknowledgement. So it thinks, okay, the data is lost. I have to retransmit the data. So this is retransmission. How exactly the Wireshark look into retransmission? And here, if you see, this is a buffer we discussed about, right? So this is a TCP buffer both on sender and receiver. So we know about this TCP window size, actual windows, calculated window size and the window size value. Once the communication happens, the buffer size keep increasing, right? So, yeah, it's keep increasing. Sender buffer and this is receiver buffer. And when we see this option, selective acknowledgement, we know that both sides of this connection support selective acknowledgement. TCP SAC should be permitted on both ends. Then instead of retransmission, the fast retransmission happens. And inside that, we know the selective acknowledgement, only the lost frames will be retransmitted. Instead of retransmitting all the packets, it's going to retransmit only the lost LOST, lost packet. So here, what is fin and reset? The fin indicates the sender has no more data to transmit. Hey, I am good to close the connection and you are good to close the connection. This is how the Wireshark looks into it. And that is called fin. We saw that in telnet session, right? So I am finished sending the data and it says, okay, I am also going to close this connection. That's a gracefully closing the connection. That is called fin. Finished, that's it. We are going to close this connection gracefully. But reset explicitly terminates a connection. Okay, if I send a SYN, and for the SYN, if I'm going to, if I'm going to terminate this connection, for my SYN, if I'm not getting a SYNAC, it is explicitly, if it goes to terminates the connection, then it is a reset. It is not interested to establish a TCP connection. So that's the key difference between fin and reset. And here, a high number of duplicate acknowledgement can be seen, where there is a packet loss and a high latency link. So then there is a latency. As I told, if you see this black coloring rule and if you see a lot of duplicate acknowledgement, then somewhere in the middle you have your link errors is increasing and you have to figure out it's a latency link. So 10.0.52.164 as for sequence number 112750. right? Because I didn't receive it. So it keeps sending a duplicate acknowledgement. So that's about duplicate acknowledgement. So this is something in the statistics. If you want to see the most active connection, the highest amount of data that's being sent between source and destination, you have to go to Wireshark. Let me open a capture for it. If we go to statistics, conversation, IPv4, this is here I got only one communication happening. Let me take one more fast retransmission. Go to statistic, conversation, IPv4. This is between only one source and destination. Okay. Let me try. So all I got between source and destinations. Let me try with other capture. Okay, let's open a new capture from my PC. Let me do a capture for my Wi-Fi connection. Let's go to statistics, conversation. Let's wait for 2 more minutes. Okay, this is fine. So let's stop this, go to conversation filter. And if you filter the bytes, so here, right? The highest talker, 1469 megabits. So you can find your talker details where if somewhere your PC is sending a lot of traffic and you want to figure out, you can figure out this. And if I go to TCP, I go to statistics endpoints, IPv4. Okay, I think I lost the subscription for the MaxPoints database. There exactly you can see where this destination is coming from. Earlier we discussed about the MaxPoint database, and then you can spot, okay, where my traffic is actually coming from which public IP address. You can spot that. So you can spot your suspicious targets with geo IP. Okay, if I get a response from this public IP address and I don't want to receive, then you can spot and where exactly it is coming from, which location, which country, which ASN number. So you'll get a bird's eye view of it. And or for all your tagged L2 packets, we discussed about the ether type. What is my next communication? Here it says my ether type, right? In ether, in the layer 2 header, I see the ether type is virtual LAN 0x8100. It says VLAN tag is next. And what is the VLAN tag used? That is VLAN 32. I found this is useful and I'll share all these images. It would be helpful for you. You can go through that. And we discussed about, dupacks and fast retransmission. Here, dupacks and fast retransmission. So that's it about the topics today. A quick, I'll rephrase everything, whatever we discussed today. So today we discussed about what is TCP keep alive, and we did a telnet session and we enable the TCP keep alive on both routers. So when exactly the TCP keep alive happens, it will not happen before your TCP connection. So from layer 1, if you see your ARP, if I get an ARP response back, my layer 3 is good, my layer 2 is good. I get an I see my layer 2, I see my layer 3. Here my layer 3 communication is happening, and top of that layer 4 comes in, and I send a SYN and I get a SYNAC back. My TCP connection established, and now I am good. And in the middle, the user is not typing something, he's takes some time. That is a human, no, I wouldn't say it's a human error, it's human is waiting for some time to type something. And TCP exactly says, hey, are you alive? I get a response from the sender. It says, hey, are you alive? You still want to make the connection open? It says, yes, I am alive, and sending in keep alive back. That's just to acknowledge on both, when both sides are acknowledging, okay, I am active and alive, and the session should be opened. I'm not yet finished with my connection. You cannot go for TCP fin for now, since the connection should be open and the user has to give some values outputs in the telnet session. So that's it about TCP keep alive and gracious ARP and how we found duplicate IP address. So every time when you connect a PC in a network, and if you assign an IP address, it's going to say, hey, it's an ARP as a broadcast. So gracious ARP, it's going to say sender IP is myself and the target IP is myself. It's going to say, hey, I am using this IP address. This is for me and nobody should use this. So that's use of gracious ARP. So other hosts in a network, so it come to know, okay, this particular IP is being used by some other host and I should not assign this IP. But even then, if you bypass it and if you assign the IP, same IP, the gracious ARP is going to say, hey, it's a duplicate IP address and I see this duplicate address from this MAC. It's pretty simple, right? So you can go to your switch, do show MAC address and find the MAC address, go shut down the port or go change the IP address. So that's how you can get rid of your duplicate IP address using gracious ARP. And you can make use of Wireshark to exactly spot your gracious ARP. And window size and calculated window size. So in the beginning, I say my buffer is 65,000 bytes. And using the calculated window size, I'm increasing the value, the multiple of the value, the scaling factor value, whatever it gives, I have to multiple with my window size value. That gives my calculated window size. So I can scale up to that. My buffer can be scaled up to whatever the multiple values the scaling factor says. That's the maximum buffer limit I have. And we have seen the lab for the same. And fast retransmissions, again, I established a connection, but instead of retransmission, if I get 3 consecutive duplicate acknowledgement, okay, my connection is still active. There is some segment that is lost in the middle, so I'm going to retransmit. I'm not going to wait for the TCP or TU, the stopwatch counter. I am just retransmitting, doing a fast retransmission. From the name, you can figure out this is a bit different from your normal retransmission. And we have seen the busy server because the retransmission happens from the client. The server is not responding. So it's very quickly you can spot it's a problem with the server. Then TCP timestamps. So what is the longest time taken in my TCP connection? You can filter out the same. We did a lab for the same. You can check that. And the use cases we discussed about, okay, what is retransmission, how exactly the Wireshark looks into it, and all those images you can go through. It would be helpful for you to spot out error in your production network. And we know what is DUPAC and what is retransmission. We discussed everything. So that's it about today's topic. And I hope everybody, got a fair idea about how exactly all the topics, whatever we discussed today, it would be helpful for you to understand, and you can replicate the same in your production network, and you can spot the problems and you can do a troubleshooting for the same. Now I'm going to stop this recording.